learning blueprint. Now the domain is the graph, the symmetry that is associated with the combination group, and it acts on the node features if we represent them as a matrix, as a permutation matrix, and then message passing, we can show that it's equivariant with respect to these permutations. Now, it is interesting that we can also have an analogy of what happens in physics, the difference between internal and external symmetries. I think actually in case of molecules, it is nicely exemplified. So we have two types of symmetries in molecules. One is the ordering of the atoms, right? So we've seen this already, so this is permutation. But we also have the placement of the graph in the space, right? So this is a geometric graph, and these are not just abstract nodes. These are coordinates of atoms in space. So if I rotate this molecule and translate it, I want my properties not to be affected, right? So basically, I want to be equivariant or invariant with respect to these two very different types of symmetries, right? So the discrete symmetries of the domain, of the ordering of the nodes in the graph, and the continuous symmetries of the features of the nodes of the graph itself, right? And this is a kind of architecture, so sometimes a little bit misleading. They're called equivariant graph neural networks. So graph neural networks are already equivariant to permutations by design. They're additionally here equivariant to continuous transformations. And this is captured again by these two symmetries, the domain symmetry and the data symmetry. And we can devise different message passing architectures that will be respecting both types of symmetries in this case. Now, these architectures actually have become very popular in computational chemistry. In drug design, probably the most famous application was AlphaFold 2, which predicted the three-dimensional structure of proteins from amino acid sequences, so that created the evolution in structural biology. DeepMind's program from a few years ago. And nowadays we also have generative models, so same way as with DALI or Midjourney, you can ask for an image. In this example of an astronaut riding a dog on the moon, and you will get a very naturally beautiful image, beautifully looking image. We can ask the same thing for other structures that are represented as graphs, such as molecules. So I can ask for a molecule that, for example, binds to some protein pocket. We can generalize these ideas to other domains, right? So we've seen convolutional neural networks applied to grids. In case of graph neural networks, we have permutation symmetry in relation to graphs. We can also work on meshes. So in case of meshes, we have a different type of symmetry, which is selection of the local frame, right? So these are discrete manifolds, and there we have what is called gauge symmetry or local rotations. And basically, all architectures that you probably use in deep learning, maybe with a few exceptions, can be viewed through this lens of the group theory and the symmetry and the invariance and equivariance. So, in a sense, any neural network architecture could be fit into this hole of geometric deep learning. Now, I will talk about graph neural networks, and as I said, graphs are ubiquitous, right? At all scales, from very small scales like molecules to very large scales, social networks, right? So spent a few years at Twitter, as Daniela mentioned, so we've been working with gigantic graphs with hundreds of millions of nodes, representing users and how they interact with each other. So when we talk about graphs, we want to represent them in a way that is digestible by a computer. So we are talking about node attributes under regular graphs. So the features of the nodes can be represented as an n by d matrix. N is the number of nodes, d is the dimensionality of the features, and the structure of the graph is an adjacency matrix, right? So it has a one at position ij if there is an edge between nodes ij and zero otherwise, right? So I'm obviously cheating here because I told you that we don't have a canonical representation of the nodes of the graph. So any permutation, in fact, is a valid representation of the graph, right? So basically, I don't have a canonical ordering of the rows and the columns of these matrices. I can permute them in any way. Now, the two prototypical types of problems I would like to solve on graphs are graph-wise predictions and node-wise predictions. The first case appears in predicting properties of molecules, as we've seen. The second case appears, for example, in social networks, where we want, let's say, to detect bad actors on the social network, so we want to classify nodes in this graph. So in the first case, I'm interested in functions that no matter how I order the nodes, produce the same output. So this is what we call permutation invariance, and mathematically this is written like this constraint. In the second case, we are interested in functions that output the same structure as the input, right? So they output some information on the nodes of the graph. So in this case, I want to be able to permute the nodes and the output to be permuted in the same way. So we are talking about permutation equivariants in this case. And graph neural networks are typically sequence of permutation equivariant layers followed by an invariant readout, if this is the problem that is required, right? Or we just leave what is called the node embeddings for every node, and then we can normalize predictions. So the way message passing works, basically every node looks at its neighborhood, it disregards all the rest of the graph, and because we don't have a canonical ordering of the neighbors, basically what we see is a soup of our neighbors in arbitrary order, right? So basically, technically speaking, this is what is called the multiset of the neighbor features, right? Why multisets? Because the features can appear more than once, right? So basically it's a set where the same element can appear more than once. Together with the feature vector of the node itself, need to be aggregated in some way by a function that we call phi, which is permutation invariant. Now, if we apply the same function at every node of the graph, right, so that's the message passing procedure, we get a function that is permutation equivariant, right? So if we change the order of the inputs, the outputs change in the same way. Now, most of the graph neural network architectures differ in the way that this function phi is defined, so we can distinguish between very simple architectures that just do linear aggregation of the node features. These are called convolutional GNNs. And in the simplest case, these node features are just transformed by some learnable matrix. So we have a linear transformation. And these are the simplest version of GNNs. They're highly scalable. They have been used in industrial applications, different social networks, including Twitter, Pinterest. Probably now everybody uses these architectures. And there are some statements about these architectures. So my favorite one is saying that they are too simple, right? So what we have here is essentially a low-pass filter. So the matrix A, the adjacency matrix here, tells us that I need to average my neighbors, and therefore I'm doing some kind of low-pass filter, so it works only in the case of homophilic graphs. So these are graphs where the neighbors are similar. So this is actually not true. And I hope to show you a result that will mathematically prove that you can obtain also different behaviors for these architectures. So another type of graph neural network is attentional GNNs, or maybe you know it under the name of transformers. So transformers are a special case of graph neural networks on a complete graph where we now aggregate the neighbor features with weights that depend on the features themselves, not only on the structure of the graph. And in the most general case, we have generic message passing where we have a general function that takes as input the features of the node and the neighbor. Now, when it comes to practically any architecture, right, you want to be able to tell how useful it is, and this is what we call expressive power. So what kind of functions can be represented by means of message passing? And there is a result, actually it was done here by Stephanie Jäger, who was faculty in this lab, who related these type of architectures to what is called the Weisfer-Lehmann graph isomorphism test. So it's a classical result in graph theory that tries to determine whether two graphs are equivalent, right, or isomorphic. In other words, their adjacency is the same after permutation follows. And it's actually interesting that this is work of Weisfer and Lehmann from the late 60s. It was inspired by problems in computational chemistry. So, they looked at how to retrieve organic compounds in large databases, considering them as compounds. So what it does, essentially, it's a color refinement procedure. It starts with a graph where every node is colored in the same way, and it examines the neighborhood of every node. So in this graph, initially, you can see that we have two types of neighborhoods. We have a node with 2 neighbors, and we have a node with 3 neighbors, right? And if I apply an injective function to them, I will be able to distinguish between these neighborhoods, so I can assign to them different labels or different colors, right? Let's call them yellow and green. So this is a new graph that I obtained by one iteration of this procedure. I can repeat it again. Now I have 3 types of neighborhoods, right? So I have a green node with 1 green and 1 yellow neighbor. I have a green with 2 yellow neighbors, and I have a yellow with 2 green and 1 yellow neighbors, right? So these become 3 distinct colors. I can repeat the procedure until the colors stop changing. I can output at this point the distribution. And this acts as a kind of graph descriptor. So if I give you another graph and I get a different distribution of colors by the Weisfer-Lehmann procedure, I can guarantee that the graphs are different, right? They're not isomorphic. But if the colors are the same, I actually don't know. So it's a necessary but insufficient condition. And we can find examples in chemistry of different molecules that are represented by non-isomorphic graphs, but these graphs cannot be distinguished by this simplistic procedure. So basically this is what we know in theory, right? So in theory we can associate the Weisfeld element test to the, basically find equivalence to the message passing neural networks and tell what the expressive power is. In practice we see that certain graphs cannot be tested by WL, and we also see that in certain situations a graph might be unfriendly for message passing, right? So imagine that in this situation, if I need to send information from the nodes here to nodes here, right? It will need to go through this narrow bridge and information might be lost, right? So basically we'll have some kind of insensitivity problem. So to address the first problem, you can resort to a hierarchy of Weisfeld element tests that are increasingly more expressive. What is called KWL tests, so they test tuples of nodes instead of individual nodes. There will always be families of graphs that cannot be distinguished by KWL. And you can design equivalent graph neural network architectures. And there have been many more expressive GNNs. The solution to the second problem, the practical one, is to decouple the input graph from the computational graph. And this is known under the umbrella term of graph rewiring. Actually, the paper that Daniela mentioned, it was also done here, so it was I did it in collaboration with the group of Justin Solomon and his students. That is called dynamic graph CNNs. So this is one of the first architectures that have explicit way of rewiring the graph. But there are many more approaches that try to do it. So this obviously creates a gap between theory and practice. So in theory, we can analyze the expressive power of a GNN only if we stick to the same input graph, right? And this is how classical GNNs operate. In practice, we can do more. So in practice, we can augment the graph with additional information. The most popular way of doing it is positional encoding. This is what routinely done in transformers. So I add some extra node or edge features to the graph. I can also lift the graph into high-dimensional topological spaces, like simplicial or cellular complexes. This is also popular in chemistry because we have a very meaningful notion of, for example, cycles in chemistry, right? So they can be represented as two-dimensional cells in the simplicial, in the cellular complex. We can also do more exotic things like look at collections of subgraphs and relate it to reconstruction conjectures in graph theory. And data symmetry, in case of regular graphs like grids, we can also have more specific message passing. So the common denominator of all these methods is adding more structure. Either it comes from the problem or we try to make it up. The second way of looking at graph neural networks is how much we trust the input graph, right? So we can, in the most extreme case, completely disregard it, and now we have a set of points, or a point cloud, and in this case we can we still have permutation symmetry. So in this case, no node interacts with each other. So we have some shared function that is applied to them. Or the other extremity is to allow any pair of nodes to interact. And in this case, we have a complete graph, and this is how transformers operate, right? So any two nodes can communicate, and usually the structure of the graph is learned based on the downstream task using attention. So graph rewiring sits somewhere in the middle. So we want basically to do message passing on a better graph, right, in some sense, rather than on the input graph. And it's a good question, what is the better graph? We can quantify it in different ways. And this actually, in my opinion, forms one of the biggest limitations of graph neural network architectures, that we somehow regard the input graph as almost a sacrosanct construction. So it conveys some information, but for message passing, we sometimes want to depart from these structures. Basically, this discrepancy between what we use for computation versus what we use as input is one of the big theoretical challenges. So I will show some results that we have on this topic, but what I wanted to show you first is basically we want some kind of analogy, continuous analogy of graph neural networks that allow to bypass this necessity to use a fixed graph. And if we compare graphs to meshes and grids, the striking thing that we see in the first two cases, I can think of a grid as a discretization of a plane, right? Or I can think of a mesh as a discretization of a surface, right? And we can think of both of them as special types of graphs, right? So a mesh is a special type of graph where we also have some additional information, right? So we have triangles. In case of grids, this is just a graph where the neighbors are connected in a certain way. we don't have this continuous analogy for graphs, and therefore we would like to develop some kind of continuous models for GNNs, and this is what we call physics-inspired GNNs. And I think Daniela's group also works on physics-inspired neural networks, so you will probably find some common topics or similarities to the work that is done here. So the way I want you to think of graph neural networks is a kind of dynamic system. Right? So every node in the graph, in this here represented in some high-dimensional feature space, you can think of it as undergoing some evolution in time, right? So this is represented by these red trajectories. So we have a time-dependent feature matrix, and the system of differential equations that govern this evolution is given here, right? So we have temporal derivative, and we have some function that applies to this feature matrix. So the layers, right? If you think of it as discretization of the time, you can think of them as timestamps, right? As discretization of the time. So we can replace the differential equation with a difference equation, right? So we take, for example, fixed time increment and then we here tau. What is the purpose of the graph? We can think of it as a coupling function, right? So the nodes of the graph, right, or these particles in this dynamic system, they don't live on their own, they interact with each other. How do they interact? Along the edges of the graph. And you can consider really a lot of different differential equations. So you can consider wave type of equations, you can consider diffusion type of equations. The most obvious thing that comes to your mind when you think of propagation of information is a diffusion equation, heat diffusion in particular. And this was really one of the first mathematical phenomena, or physical phenomena that was formalized mathematically by none less than Sir Isaac Newton himself. So in a paper that he published anonymously in the Transactions of the Royal Society, he described what nowadays we know as the Newton's law of cooling, that tells you that the temperature of a hot body that it loses in given time is proportional to the temperature difference between the object and the environment. Right? And basically he described an experimental setup and a mathematical model that captures this phenomenon. So here is how Newton's law of cooling can be applied to graphs, and this is a very general law. You can apply it to diffusion of heat, you can apply it to chemical diffusion, you can even apply it to propagation of rumors on social networks or infections in some population. So this is how it looks like. So let's say that we have some temperature in the nodes of the graph, right? It is denoted by this feature vector x. So the rate of temperature change is the temporal difference, right? So x dot. The temperature of the object itself will be the feature at node I. And then the temperature of the environment will be some weighted average of the neighbors, right? So basically this is a local differential version of the Newton's law of cooling. Now allow me to rewrite this formula slightly, so I can write it like this. So what is written here in the parentheses is a graph version of the gradient operator for classical calculus that I hope everybody knows. Basically it looks at the difference between the features and the endpoints of an edge. Right? Now what is written here, this summation, is the graph analogy of the divergence. So if the gradient takes me from nodes to the edges, the divergence does the opposite, right? So it collects the information on the edges that share a node, right? And sum it up into a new node feature. So in mathematical terms, they are called formally adjoint operators. So together, the divergence of the gradient or minus divergence of the gradient, depending on the notation, is called the Laplacian or Laplace-Beltrami operator if you come from differential geometry. And here we get the basic version of the heat equation. Homogeneous is called the heat equation. So basically what it tells you is that my evolution of the temperature depends on how different I am from my neighbors. Right? Now, what also we know about heat equation, that it's a prototypical example of what is called the gradient flow. So gradient flow is a continuous version of steepest descent, right? So it's an evolution equation that you can write as descent in the negative direction of the gradient of some energy. And we also know how this energy looks like for in the case of heat equation. We call it the Dirichlet energy in physics. So this is this quadratic form that essentially looks at how different you are from your neighbors. It is zero if the signal is constant on the graph, right? So if all the nodes are the same. You can think of it as a kind of smoothness of the node features, and we can also show that it is monotonically decreased along the flow. So if I run the heat equation, the Dirichlet energy will be becoming smaller, and in the limit, it will result in oversmoothing. So in terms of dynamic system, the oversmoothing looks like so all the features in all the nodes will collapse into a single point, so they will become all the same, right? So it's not necessarily a malignant behavior, so often in the literature you describe oversmoothing as something bad. But actually, if the graph is homophilic and you have some boundary conditions, if you know the labels of some nodes, you can just diffuse these labels and it works remarkably well. If the graph is not homophilic and you have some missing features, some other situations, then of course you need to do something smart. Now, why I'm mentioning gradient flows, if you think again from the perspective of these dynamic systems, the classical approach in designing GNNs, you can think of it as you start with the system of differential equations, right? You discretize them and you parameterize every iteration, right? So it now corresponds to a layer of a neural network, so for every layer you will have a different set of fluids. What I'm suggesting is to do something different. So you start with an energy, you parameterize an energy, and then you derive the evolution equation or its discretized version as a gradient flow. And what it gives you, of course, not every evolution is necessarily a gradient flow, right? It will impose certain constraints. So basically it results in some kind of architectural choices that you need to make about your graph neural network. What we get in exchange is better interpretability. And what I mean by interpretability is kind of a bad word in machine learning. What I mean by this is that we will be able to make some statements about the behavior of these systems. And one particular example is this. So we said that there is this folklore statement that convolutional graph neural networks are unable to deal with heterophilic graphs. So this is how a heterophilic graph looks like. So all my neighbors are of different color, right? So the color here represents the label. The position of the nodes represents some two-dimensional toy features, right? So you can see that actually here we can find trajectories that separate the reds and the blues, right? So the task here is node classification. You can see that we can perfectly separate. And the energy here is some generalized parametric version of the DHA energy. So we have also the channel mixing. And basically, from physical perspective, what we have here is the interactions between particles that attract along the positive directions of positive eigenvectors of the channel mixing matrix W and repel along the negative eigenvectors. And the evolution equation is this convolutional type neural network, right? You see why it's convolutional, because the way that the information is propagated on the graph is dependent only on the structure of the graph and not on the features, right? So again, right, there's a linear matrix multiplication. And the theorem is that in this kind of architecture, I can avoid oversmoothing if I choose the matrix W appropriately. In particular, it must be symmetric, so this guarantees that it's a gradient flow, and it must have sufficiently large negative eigenvalues, so I have not only smoothing, right, not only averaging, but also the sharpening or the repulsion. Okay? So this contradicts the GNN folklore, and we have other results of this kind that go along some incorrect facts that are repeated in the literature. Now, if you think of from this perspective of differential equations, right? So let's see how we discretize differential equations in the plane. We have basically a continuous operator, the Laplacian, right? And on the grid we can represent it in different ways, right? I can discretize it in many different ways. Any linear combination of these operators is also a very discretization of the Laplacian. So we don't have really a canonical graph, right? Computational graph when we discretize differential equations. In fact, we can apply the same idea to graph neural networks. And allow me to skip the details. Basically, we can have an evolution that considers the graph also with positional coordinates. We can evolve together by some type of diffusion equation the features, the positions, and also rewire the graph based on the positional coordinates. So you can see all the three phenomena happening here at the same time. So we have the features evolving, we have the positional coordinates evolving, and the graph changing at the same time. And it is also interestingly related to Ricci flows, and as you probably know, this was mathematical tool that famously was used to prove the Poincare conjecture about 15 years ago by Ray Perelman. And what does it have to do with graphs? Basically, we can evolve the graph by an analogy of a discrete analogy of Ricci flows, where we can attribute undesired phenomena such as over-squashing or loss of information in a graph neural network to the presence of strongly negative curvature. So, by the same way as we can define curvature on manifolds, we can define an analogy of Ricci curvature on graphs. Basically, it's a combinatorial construction that counts a number of triangles and rectangles, and we can distinguish between something that locally looks like a clique or a grid or a tree. And the main result informally is that it's the presence of negative edges, negatively curved edges that is unfriendly for message passing. So we have basically a way of measuring how the graph is good for message passing, and we can remove the negatively curved edges, replace them by edges with positive curvature, allowing us to improve the performance of graph neural networks. Now, in this consideration, we didn't consider the task at all, right? So we can say whether the graph is friendly for message passing, right, based on its topology that we can characterize locally using this curvature. We can also write bounds that relate to the architecture of the graph neural network, right, like number of layers, some bound of parameters. We say nothing about the task, and this is actually very important because I can give you exactly the same graph, exactly the same features, but different tasks or different functions that I want to compute on this data set, and depending on this task, the graph could be either good or bad for message passing, right? And a good example again comes from chemistry. So in the molecule, I have different types of forces. So I have van der Waals forces that decay very fast, and I have electrostatic or colonic forces that decay very slowly, right? So in the very fast case, I can easily use the given graph, right, and basically everything is local. In the slow decaying case, I probably need maybe a complete, fully connected graph. So this is again to show that we have the same graph, the same features, two different tasks, and whether the graph is good for message passing depends on the task. So the way that we can characterize it, and again allow me to skip the details, we can characterize the task, right, or the function that we compute on the graph and its features through what we call mixing, so it's some bound on second order derivatives. And we can relate the three things that we have in the graph neural networks: the characteristic of the function, characteristic of the model, right, the architecture itself, how many layers, and so on, and the topology of the graph. And basically this comes in the form of some capacity bounds, so I can make statements about a given architecture that do not resort to Weisfeld element anymore. So I can, for example, have these kind of negative results. I can say that a message passing architecture with L layers cannot learn tasks that have high mixing if the graph has a large commute time between the nodes. So basically it bundles together all these three components that we have in graph neural networks. Allow me, in the interest of time, skip the dynamic message passing part, which is cool, but unfortunately I don't have time. Let me talk about some applications. And I think if you ask for one single application where graph neural networks and geometric deep learning has been successful and actually created an entire new zoo of architecture, this is applications in computational chemistry, in particular in molecular design. So you probably know that in our body everything is governed by proteins, right? So this is what is encoded in our DNA, and proteins appear more or less in every important biochemical system, from transporting oxygen to our cells, defending us against pathogens, making possible chemical reactions, right? Enzymes, basically natural catalysts that make reactions happen. Even the elasticity of our skin is because of a special protein that is called collagen. Now, proteins are basically they're biopolymers, so they are sequences of amino acids that look like this. So the amino acids share the same structure that is called the backbone that is connected into the sequence, and then they have different residuals that are called the side chains. And under the influence of electrostatic forces, this chain folds into a complicated three-dimensional structure that is typically visualized like this. And this has been the holy grail of structural biology, to be able to predict the structure of the protein from its amino acid sequence. It was postulated in the 70s that we can do it, but it took almost 50 years to actually achieve it, and that was the famous AlphaFold. So when we try to design new drugs, we are interested actually in the opposite problem. So we would like to create a protein with some structure, because structure is what endows protein with function. A good analogy here is a lock and the key. So same way as we have a unique key that can fit into a lock and match the knobs inside the lock that will open it, I have a protein that has certain holes or pockets in it, and it can fit exactly one particular molecule, right? And I want to be able to find the right molecule that will fit into this hole, or maybe this molecule can also be another protein. So this is how biological drugs work. So the drug itself is not a small molecule, it's another protein. Now, if you think of proteins, we have basically three levels of representation. So we can think of them as sequences of amino acids, and some of the early techniques in bioinformatics looked at them as strings, right? So it's very appealing, it's one-dimensional structures. You can think of them as text. Then the sequences of amino acids, right, they fold into structures, and the structures give the protein its function. For example,
what molecules it binds. So we had a lot of experience with representing proteins as surfaces. So basically, you think of it as a mesh or as a manifold, and then you can use geometric deep learning architectures that can be run on the surface itself, right? And this was a framework that we developed with collaborators from Lausanne, the PFL, the group of Bruno Correa, and we used it to design different proteins. We had different anti-cancer proteins that bind, for example, PD-1 or PD-L1 targets that are used in immunotherapy. We also developed binders for the spike protein of the SARS-CoV-2 virus, right, the one responsible for COVID-19. So here is an interesting example with molecular glues. So we have proteins that interact only in the presence of some molecule. And what we really want to do is a generative model, right? So we want, the same way as we can generate images in response to some prompt, we would like to generate proteins or maybe small molecules that have some properties, right, that we can describe. And generative models, basically mathematically what underpins them is an ability to sample points from distribution, right? So you have some high-dimensional distribution of your data, you want some kind of mechanism that allows you to sample from. The problem with approaching it naively is that you are bound by the curse of dimensionality. It is very difficult to model high-dimensional distribution. So what is being used in diffusion models that have become popular about 5 years ago, even though the concepts date back earlier, is you start with some data and you gradually add noise to it. So mathematically, this can be described as a diffusion equation, right? And this is how it looks like. So it's a stochastic differential equation. It has a term that is called the diffusion term, right? So this is Brownian motion, and it has a drift term that is the signal itself, and alpha and beta are functions of time that are scheduled in such a way that you start with a signal and you end up with no signal and pure noise. So what you try to do is you try to reverse the diffusion process, and the remarkable property here is that the reverse process is also a diffusion equation with different coefficients. What is you cannot compute is the log of the probability, so you can use a neural network to approximate. And this is how diffusion models work, and they achieved remarkable results in recent years in generating very realistically looking images and other examples. So this is how it looks. So you start basically with Gaussian distribution, and you sample a point and you go back. You reverse the diffusion process, and what you get is some sample from the data distribution. You can run this process multiple times. You will get different samples. There is an alternative class of approaches that are called flow matching. So in this case, you try to map one distribution on some geometric domain to another, right? So you have the source that let's call it P0 and target P1, and you have some warping, right, or technically diffeomorphism that is time dependent. So basically a continuous trajectory from one distribution to another that you can obtain through the push forward by this diffeomorphism. Now you can the flow itself, basically you can describe it by this equation with some initial conditions, and again here you have some kind of vector field that usually you cannot compute, but you can approximate. You can learn it with the neural network. So these are two competing approaches. Flow matching probably is a more general approach because you can map any distribution to any distribution and on any geometry. In fact, there are many recent works, including our own, and including works that have been done here in the group of Regina and Tommy on using techniques from Riemannian flow matching on some exotic manifolds that describe protein backbone structure. We also have recent papers where we can, even in Euclidean settings, we can learn the magic, and then we have magic flow matching, which provides better generalization. So we have trajectories that do not go outside of the support of our data. Or finally, we can also do flow matching for categorical distributions, basically by thinking of distributed probability on a simplex and then mapping it into a hypersphere, or again, you can use Riemannian flow matching. Let me skip this because I'm almost out of time. So let me show you examples for proteins, and this is actually again, the work that I mentioned, the inspiration came from the work of Gabriele and Hannes. We can think of our protein backbone, right? So this chain of amino acids, in terms of local reference frames, right? So basically, we can represent the atoms in these frames, and then the protein is represented as the relative positions of these frames that can be thought of as elements of this group SE3, especially Euclidean group. So it includes rotations and translations, no reflections. Reflections actually change what is called the chirality, or basically the effective chemical properties of the molecule. So we always exclude reflections, and we have only rotations and translations. So together, the protein that contains n such amino acids, we can think of it as basically as an object, which is a product of these special Euclidean groups. So it's a high-dimensional manifold, and we can do flow matching on this manifold. So we have this architecture that does flow matching. We can condition it on the sequences, and we can generate new proteins. We can show that actually we get proteins that are designable, that are more likely to be synthesized in practice. They are also more novel. So here it is the TM score represents similarity to proteins in the protein database on which the model was trained. So this is actually an interesting plot. So the blue line here is the previous best result. This is Rosetta flow diffusion. So this was monumental work from the group of David Baker at the University of Washington. Recently, if you followed the news, they got $1 billion investment in a company that is using Rosetta flow to design presumably future drugs. So our model is actually significantly better, at least in this benchmark, and we didn't receive $1 billion investment to develop it. Well, you know, it's still it has to be still validated experimentally, but I think the results are very, very promising. Here is another example. So this is what is called motif scaffolding. So when you design drugs, you typically have some target and you have some little protein fragment that is complementary geometrically and electrostatically to the target. So you want to keep it. This is called the motif, but then it is not stable on its own and it's not specific enough. So you want basically to build a bigger protein that has this motif. So we can constrain our generative model in a way that the motif is always preserved, and then the scaffold is generated around it. And again, this is a difficult task, and this is one of the important pieces in design of proteins that can be used as biological drugs. Here is another example. So zero-shot molecular dynamics. As you know, proteins are not just static bricks, so they quantum mechanical systems, so they wiggle all the time. And we can use molecular dynamics to simulate different conformations of the protein over time. But this is a very expensive process, so again, we can use generative model to basically to replace molecular dynamic simulation. And you can see that with this architecture foam flow, we can actually do it significantly better than previous approaches. Finally, last application. So this is actually a company I'm involved in. I'm chief scientist of Plant AI. So they are building molecular glues. And molecular glues are a very interesting modality of therapeutics that bring proteins together. And in particular, one mechanism is what is called protein degradation. So you bring your target close to a catalyst, right? This is called E3 ligase that degrades the protein using natural mechanism of the cell. So basically, you destroy your target, and this way you can cure diseases that are otherwise incurable. The way that molecular glue is designed, it has a part that binds to the protein, another one that binds to the ligase, and some bridge between them. So you can think of it as a problem of molecular paintings, right? So I have some fragments that I know their structure, and I want to connect them. So here, again, we can use a generative model that connects these fragments together, and we call it diff linker. So this is how it works. So we have these fragments, and we have the generative model that generates a way of linking them, and we can do it with multiple fragments. We also have some experimental validation that show that the molecules that we create do actually bind the target proteins. Now I should say that it took us a lot of time to publish this paper. It was rejected, I think, from all machine learning conferences, so it ended up in Nature Machine Intelligence. Yeah, sorry, that's not exactly the venue where you publish machine learning papers. But one of the co-authors, Max Welling, he now has a startup that looks at climate change and carbon capture. So they try to design new materials that will be able to bind carbon and extract it from the atmosphere. So he sent me this paper saying that actually in this field of carbon capture, so there is a special type of materials that are called metal organic frameworks. So these people have been using our deep linker for quite some time. So it's been out for more than 2 years. So it's, I think, especially for the students here, so you never know where your work will end. So we were unable to convince people in machine learning communities. So we received reviews saying that the problem is not realistic and not interesting, even though probably half of the drugs are designed in this way, fragment-based drug design, but apparently it appealed to people doing completely different problems in completely different fields. So I would like to conclude. I hope that I convinced you that geometric deep learning is an interesting tool, both for molecular modeling, but probably in general as a perspective on machine learning problems. And I started with a quote. I would like to finish with a quote. This one is from Helvetius, who famously said that the knowledge of principles compensates for the lack of knowledge of facts. And basically that's the message that I want you to keep, that you can design deep learning architectures from first principles, which are invariance and symmetry. So thank you very much.
Some questions, but let me start by asking one. There are so many students who are so eager to make an impact with machine learning. What is your advice to all the students in the room? What are the fundamental building blocks that they should be looking towards, and what applications are most likely to be happening around the corner? And especially, this is especially in the context of the discussion we had at lunch, where we talked about how we really want machine learning with better properties.
Yeah, very well. I have my biased opinion. I think AI for science is very interesting, and that's probably where the impact of machine learning will be tangible and real, and probably will change the way that we do science, potentially. So we see already, well, in biological sciences, we see a big impact. AlphaFold is probably the most prominent example, but there are many more. In different fields of science, like climate or weather, basically something that has required supercomputers and simulations that solve systems of differential equations. Nowadays, it seems, at least some very promising works show that you can replace it with generative models. So it allows potentially to completely bypass the slow and inefficient and non-scalable components that have in these fields. So I don't take it as an advice, because this field is it's ungrateful to make predictions, but I think it also has very good cause behind it, right? So whether it's drug discovery, so we like to cure new diseases, or maybe we want to counter climate change with carbon capture or similar technologies, I think I would like myself to work on these problems.
Okay, one more comment, one more question in the same line, and then it's all yours. Do you have suggestions, or what are your favorite bite-sized open problems? Not the big ones, but bite-sized.
Well, in machine learning, I think generalization is a big open problem in different flavors. So understanding it better, well, in case of these kind of architectures so that incorporate geometric priors, there are many interesting flavors to it, especially when you have you assume some symmetry, but the symmetry that you build into an architecture is different from the symmetry that is present in the data. So yeah, I would say this is probably really the important question, because that when you deploy a machine learning system, you will apply it to data that you've never seen before, and all the problems arise when it behaves in a way that is not expected.
What do you think about the fact that most of the models we deploy are fixed, and so we deploy them, and if we want any changes, we need to wait for the next release. What about bringing some sort of adaptation in our solutions?
Well, it is done. So there are ways of doing it. You run into other problems like what is called in some literature, catastrophic forgetting, right? So you want to be able to update the model without forgetting some important previous information. So yeah, I think this is also still an open problem, how to do it properly.
All right, questions from Michael? Yes, go ahead. Speak loud, please, so we can hear.
So you mentioned the importance of principles as well, general principles that can make up for a lack of knowledge, and you mentioned the importance of incorporating geometric priors. And I have a prime example of molecules, protein structure prediction, and then maybe even like the treatment of frames and fold flow, and yeah, maybe frames were even introduced by AlphaFold 2, and then what do you think about something like AlphaFold 2 being completely superseded by AlphaFold 3, which ignores equivariance completely and literally has neural networks that take 3D coordinates as inputs and does diffusion on them?
Yeah, so I was expecting this question for you. So, well, just for the audience, so basically AlphaFold 3 that was recently released by, well, actually the model was not released, it was announced, and there is a little bit of a glimpse of what it does. Basically it replaced the geometric architecture, the invariant point attention that was used in AlphaFold 2 by what they call an all-atom model, where you just, basically it's just a big transformer where you do data augmentation to account for rotations and translations of the molecules, and then you basically you just work with you predict the three-dimensional coordinates of the atoms. So I think there are two things. So one of them is certain things that happen at small scale, certain problems that exist at small scale disappear at large scales. You get other problems, and we probably we've seen it with NLP, right? And this is probably what we see in biological problems. I'm not sure that the scale of the data that we have now in these problems justifies it. The second problem is the hardware lottery, right? So the phenomenon that it's not always the best algorithm that is used. It's the combination of the algorithm and the hardware. And in this case, transformers map nicely to GPUs. The equivariant architectures are slightly more difficult to implement, even though NVIDIA has succeeded doing it very well. There are other reasons. I think they wanted to deal with all types of biological molecules, so RNA, for example. So the frame-based representation doesn't work there. So I would say this is probably more pragmatic reason for doing it. I don't know. I think that we still want to do geometric architectures. Maybe the equivariance is not necessarily need to be hardwired into the architecture, but it can be introduced in some gradual or soft way.
Thank you. Next question. Go ahead.
Hi. Fascinating work on molecular generation. I don't know if you ever met Pat Walters, who is he recently posted a review of DeepLinker. So my question here, in these models, should we focus on also incorporating the ability to synthesize these molecules and making sure that the rings, the structures that have been predicted are actually stable and can exist in real life? Because that's a big problem. We can make the perfect structure, but we won't be able to make it.
Yeah. So well, we had a paper at this idea on basically on the diffusion models for retrosynthesis. So that to some extent account for it. So there are several works. So in Cambridge, the group of Pietro Neo has students that are working on basically you parameterize certain templated reactions. So you have some reagents that you can buy, for example, from enamine, right? And then certain reactions that you can implement with some lab robot. It of course restricts a lot to the space of reactions, but this way you can guarantee that you can actually efficiently build these molecules. You can probably do it in other ways, so you can maybe penalize for lack of synthesizability. So there are different metrics for it, but I guess probably not a single solution. There are many ways of dealing with it.
Next question. Don't be shy.
When you're dealing with molecules, do you sometimes feel sad that there are so few symmetries to account for, like permutations and acid-free? Meanwhile, like tests, for example, I think deals with lots of symmetries that I don't understand.
You mean in high energy physics, right?
Yeah.
The complex codes well. No, I don't know these problems well, so maybe you can comment on this. But You can also combine different symmetries. So, well, unrelated to molecules, we have works where we look at product groups, and this is related to subgraph GNNs. So we can look at basically it's more general idea. This was actually an idea that comes from Guy Maron. When they have, for example, a collection of objects that in their own term they have symmetry, like collection of images. So you have the translational symmetry associated with each image, and they have also permutation symmetry associated with the ordering of the images, right? And you can think of more complicated things, right? So you can think of graphs within graphs, and so on. So you basically can design architectures that work on this combined or product symmetry group. So in case of subgraph GNNs, it's the permutation of the nodes and then the permutation of the subgraphs that you extract from the graph, and we can show that these architectures are probably more powerful than WO test. So there are more exotic things with also different types of products. So it's not that boring as you described.
All right, let's one quick question, last question.
In the context of drug discovery, like machine learning seems to be something a little more like generation of molecules or
A
confirmation.
little bit louder, we
Oh,
can.
in that sampling and like generation sense, less so the like molecular force field for dynamics, for example. And I'd like to ask, what's your view on the importance of molecular dynamics in the future in the context of drug discovery? Because it's also one field where ML is trying to address its like force field, but also it's very costly, a lot slower, and also hard to validate. So, what is your viewpoint on molecular
Can you
dynamics?
repeat the question?
Yeah, so molecular dynamics, basically, what's the future of ML for molecular dynamics, like ML machine learned potentials. So I'm not an expert in molecular dynamics, so take it with a grain of salt. I believe, or I hope, it will be superseded by genetic models. These are basically very computationally heavy tools that have been used for many years, and some physicists don't trust molecular dynamics, for example. So it depends on this magic how you create your potentials. So maybe it's not needed. I know that many people will kill me for saying this.
Let's give Michael another warm round.